Okay, well, I think we'll make a start. My name's Colin Kilcorfield. I'm the head of department of the Department of Applied Maths and Theoretical Physics here in Cambridge, or at least I'm here in Cambridge. And it's my great pleasure and honor to be hosting you all here today for the 14th annual Andrew Chamblin Memorial Lecture, which will be given by Professor Alan Guth from MIT. Thank you very much all for coming along, and of course thank you to Joe Ashbourne for organising this, or helping to organise this. Just a little bit of housekeeping to start with. We are recording this lecture, so please be aware of that in terms of interactions with the recording. If you wish to ask a question, please use the Q&A facility rather than the chat. And if the chat you please just use the chat for IT problems. We as panelists can see both, but it would be easier if all the questions are only in the Q&A, and I'm sure Alan will be happy to answer them at the end. In terms of where will the recording be available, it will be available somewhere on the DAMT web pages. And I'm sure that we will then distribute the link when it is loaded up via the mailing list we have collected of the people who have signed up for this lecture. So, of course, this is the 14th Memorial Lecture for Andrew Chamblin. So we should, of course we will continue to remember Andrew. Andrew was a brilliant physicist. Got his undergraduate education at Rice. He was born in Lubbock, Texas, and then went to Rice University. Then came to the UK, went to Oxford for a year to work with Roger Penrose, and then came in 1992 to St. John's College here in Cambridge to do a PhD with Gary Gibbons and Stephen Hawking. And it's entitled Aspects of Topology in Classical and Quantum Gravity. And really excellent thesis. He then got the prestigious Draper's Research Fellowship at Pembroke College, Cambridge, and then several other postdoctoral jobs before getting a faculty position at the University of Louisville. And then tragically and suddenly, he died on the 6th of February 2006. And his friends in the physics community all over the world got together to fund in perpetuity this highly prestigious lecture, of which this is the 14th, and also an organ recital in Oxford. And it is an honor for the Department of Applied Maths and Theoretical Physics to host this, and even in the virtual way that we're able to host it this year, it is still a great pleasure to be able to do this. And to continuing the tradition of having very eminent physicists come to give this talk, we're greatly privileged to be able to hear Professor Alan Guth from MIT to talk to us today. He is, of course, the Weisskopf Professor of Physics at MIT. He got all his degrees at MIT and has had many prizes and awards, including the Breakthrough Prize in Physics, the inaugural time they were awarded, and also the Kavli Prize more recently in 2014. So we're really looking forward to hearing what Alan has to say. And so that's enough of the introductions from me. And so over to you, Alan. Let's see if we can get this tech to work. Great.
Okay, hello everybody. It's a great pleasure to be here to speak as part of this Andrew Chamblin Memorial Lecture Series. I'll be talking today about infinite phase space and the two-headed arrow of time, which is a proposal for an answer to the question of what drives the arrow of time, how did it originate? Might add that Andrew Chamblin was a postdoc at MIT from 1999 to 2001, and I knew him very well. We had a common interest at that time in possibility that the universe might live on a membrane in a higher dimensional space, which is certainly still a possibility. He was a truly wonderful person, a wonderful friend. And when I learned that he passed away in 2006, it was certainly a tremendous loss. And I think it's very fitting that this series of lectures is going on in his memory to keep his memory alive. The work that I'll be talking about today is work that I've been involved in a collaboration with Sean Carroll and Shan-Yao Tsang. We, in fact, have been planning to write a paper about this for many years and have somehow not gotten around to it, but someday we probably will. In any case, I'll describe today our thoughts on the subject. The key issue, as probably many of you are aware, is the fact that in the real world, when we see things happen, the sequence of time is extremely evident. For example, if we watch an egg break, if you look at those 5 photos, nobody would have any doubt about what order those photos occurred in. For real events, the ordering is very, very clear. There's a well-defined arrow of time that we all recognize. On the other hand, if we look at the laws of physics, they appear to be completely time symmetric, exactly the same in one direction of time or the other. In saying this, I should probably qualify it a bit. I'm sure many of you are aware of CP violation and the belief that CPT, charge conjugation times parity times time, is an exact symmetry of nature. And that means that T, time reversal symmetry, is violated. And experimentally, it's violated in extremely weak decays in the K meson system that are certainly not a part of our everyday life, but nonetheless do violate the symmetry that particle physicists call T symmetry. However, from our point of view, we still claim that the laws of physics really make no distinction between the past and the future, none whatever. And the point is that CPT itself, which is believed to be an exact symmetry, and there's nothing we know that might contradict that, can be taken as a time reversal operator. It does mean that for every state, there exists a corresponding time reverse state, which will evolve along exactly the same trajectory as the original state, but backwards in time. The only catch is that to construct this time reverse state, you have to not only change the particles to antiparticles and reflect the whole thing in a mirror to implement the parity symmetry, but you have to also show the movie, I'm sorry, I'm not saying it's right. Yeah, the point is that you have to carry out those 2 operations. It's not enough just to reverse the momenta. You have to also change particles to antiparticles and reflect in the mirror. But nonetheless, there does exist a state which will follow the original path exactly backwards, making no distinction, therefore, between one direction of time and the other. So if the laws of physics don't make any distinction, but we see this clear distinction, obviously that raises a big issue of what is causing this. Feynman, in his lectures on the character of physical law, says quite a bit about this, and this is an exact quote. The most obvious interpretation of this evident distinction between past and future, and this irreversibility of all phenomena, would be that some laws, some of the motion laws of the atoms, are going one way. There should be somewhere in the works some kind of a principle that Uxels only make Wuxels, wonderful Feynman language, and never vice versa. So the world is turning from Uxley character to Wuxley character all the time. And this one-way business of the interactions of things should be the thing that makes the whole phenomena of the world seem to go one way. That's followed immediately by but. We have not found this yet. That is, in all the laws of physics that we have found so far, there does not seem to be any distinction between past and future. So that basically is the problem that we're trying to address. Now, we do know a lot of things about this that are generally agreed upon, although we don't although there's controversy and uncertainty about what causes the arrow of time, we can describe it. Ordered systems tend to evolve into disordered systems. So the world is turning from an ordered state to a disordered state, which is, I think, the more detailed version of Feynman's Uxley to Whatsley. The measure of disorder is entropy, and we do know how to define it and use it. And the fact is that we always see entropy increase and never see it decrease. And that, of course, is the famous second law of thermodynamics. So all of this describes the arrow of time without trying to explain how it originated or why it happens this way. The classic example of the growth of entropy is a gas in a box. This is a standard example in textbooks. If a gas is placed in the corner of an otherwise evacuated box, it will spread to fill the box. And as it does that, entropy increases, disorder increases. Once the box is filled with the gas is in equilibrium, and it will then stay in that state of maximum entropy in principle forever, although there will be random fluctuations about that state. The opposite motion in the opposite direction of time, where all the molecules suddenly return to the corner of the box, is certainly a possible motion, but it's highly unlikely that the positions and velocities of the gas molecules will be just in the right configuration to do that. So statistically, we don't expect that to happen, although if we wait long enough, it will happen. But it's a phenomenally long amount of time that would have to be waited. So statistically, we do understand how highly ordered states are likely to become disordered. But that still leaves the important question: if we think of this box of gas as a metaphor for the universe, how then did the universe begin in this highly ordered, low entropy initial state, the state that's the analog of all the gas being in the corner of the box? So one possibility that was considered at least as far back as Boltzmann's work in 1895 is the question of, could this low entropy initial state have just been a rare fluctuation in a system that was actually in equilibrium? Boltzmann discussed this in a paper in 1895, published in Nature. I think it's rather fascinating that a journal that Boltzmann published in 1895 is still one of the world's leading journals. Boltzmann's answer was yes. He said, assuming the universe is large enough, the probability that a small part of it that would be our world should be in its present state is no longer small. If the universe is big enough, somewhere you might expect there'd be a region as large as what we see that would just happen to have fluctuated into this highly unusual state. Unusual things happen if you have enough chances. That idea is disputed by most modern physicists, and I believe it's wrong. Feynman wrote in this same article in The Character of Physical Law in 1965 that the answer to this question really is no, not what Boltzmann gave. The important point is that if the order in the universe were just a fluctuation, then we would definitely not expect it to extend so far out into space. Boltzmann was right that we don't know how big the universe is, so no matter how improbable it may be for a galaxy like ours to form as a fluctuation, it may still be likely that it happens somewhere. But, Feynman argued, we still know something about relative probabilities. The point is that it would be vastly more likely to form an isolated galaxy surrounded by a gas and thermal equilibrium than it would be to form two galaxies. And the probability of seeing 10 to the 11th galaxies that all seem to be very far out of thermal equilibrium, which is what we see in the visible region, is really just too small to even think about. It's not what you would expect to happen. If we were formed out of thermal equilibrium, we would expect to see a very small region that we'd be part of, and outside of that, we would still expect to see thermal equilibrium conditions. So what Feynman settles on, and what I think is the conventional wisdom here, is that for lack of any other explanation, we have to simply assume that the low entropy initial state of our universe was fixed by whatever unknown physics determined the initial conditions of the universe. And we really don't know the initial conditions of the universe. As you're probably aware, I've spent a lot of my life working on the theory of inflation. Inflation is not really a theory of the origin of the universe. Inflation is really just a theory of the very early evolution of the universe. So as long as we don't know how the universe actually originated, we're certainly free to just hypothesize that something caused it to begin in a very low entropy state. And that, I think, is the conventional wisdom on this subject. Today, I'll be suggesting an alternative to that conventional wisdom. One question is what I just vaguely alluded to. Could inflation be the solution to this problem? Does inflation explain the arrow of time? And I've shown here a pretty picture, which was designed mainly to prove that I know how to download pretty pictures from the web. The pretty picture starts with inflation on the left. It's a timeline going to the right. At 375,000 years, the cosmic microwave background decouples from the rest of matter and is essentially released. Then there's a period sometimes called the Dark Ages where nothing happens. Then stars and galaxies start to form. And then later the universe starts to accelerate it again under the influence of dark energy. So this is the basic timeline, beginning with this burst of extremely rapid, essentially exponential expansion called inflation. Early on, people debated whether or not inflation by itself can solve this problem. The first person to weigh in on this that I'm aware of was Paul Davies, who wrote a letter, again to Nature, in February 1983 with the title Inflation and Time Asymmetry in the Universe. The title was neutral, but the abstract contained these words. The recently proposed inflationary universe scenario explains several of the mysteries of modern cosmology. I argue here that it also provides a natural explanation for the origin of time asymmetry, time's arrow, in the universe. So Davies was arguing that inflation, by expanding the universe by a huge amount, sets into motion the subsequent growth of entropy. Davies' article was immediately refuted by Don Page. Here's a picture of Don, I think, gloating about a bet that he won with Stephen Hawking. About 6 months later, in July 1983, Don Page wrote an article for which the title was Inflation Does Not Explain Time Asymmetry, excuse me. And his abstract read as follows. Davies has argued that the inflationary cosmological scenario provides a natural explanation for the time asymmetry of the universe. Here, I dispute this argument by noting that the inflationary scenario implicitly invokes time asymmetry with the assumption of the absence of initial spatial correlations. I don't quite know what that means, to be honest, but that's what he said. No scenario based on CPT invariant dynamical laws can explain the time asymmetry apart from postulating or explaining these initial conditions, as Penrose has emphasized. So I would say, by the way, that I think Paul Davies' article is by no means a complete explanation for how the arrow of time was set. But I also think that Don Page's refutation here is not really accurate either. And in particular, I want to focus on these words that Page wrote. No scenario based on CPT invariant dynamical laws can explain the time asymmetry apart from postulating or explaining these initial conditions. Sean Carroll and I and Xin strongly disagree with those words. And most of the rest of the talk today will be devoted to explaining how we think, why we think those words are wrong. So the proposal that I want to advertise is the proposal of a spontaneous two-headed arrow of time. A few references first. The original source of this idea is a paper that Sean Carroll wrote with Jennifer Chen back in 2004. There are some other important references. Julian Barber with collaborators has his own version of a two-headed arrow of time. We agree completely on the feature of the two-headed arrow of time, and I think it appeals to us both for the same reasons, that allows one to describe how an arrow of time can arise in a universe where the laws of physics are completely time symmetric. Aside from that, there are very different theories, as I said in my title, and as you'll see the reasons for it in a minute, our view, Sean Carroll's and my view, depends crucially on assuming that the total phase space volume that the universe has available is infinite, while Julian Barber wants the opposite to be true in his point of view. So they're very different points of view, but nonetheless, two different versions of a two-headed arrow of time. Other articles I wanted to mention, my colleagues at MIT, Gliorso and Hong Liu, wrote an article a few years ago about the second law of thermodynamics from symmetry and unitarity. That paper does not really address the origin of the arrow of time, but it does address the question of how we know that entropy will never decrease and will grow if the initial state is not at the maximum entropy. Similarly, Raphael Busso, in the context of inflation, wrote an article earlier, which I think basically shows the same thing in this other context. There should be an upcoming paper by Sean Carroll and Xianyou Tsang and me. I have to admit the paper has been upcoming for the last 8 years at least. We have made the press, so there's some evidence of our having been involved in this. So two articles here I want to mention from Scientific American and from New Scientist that talks a little bit about the ideas that Sean Carroll and Xianyou Tsang and I have been tossing around, which is what I'll be talking about today. So what is the proposal? The key idea is to make the assumption that the maximum possible entropy for the universe has no bound, is infinite. We don't claim that we know that this fact is true, but has to be either infinite or finite, and we don't know either way. So we want to pursue the assumption that the maximum possible entropy is infinite. And we do find that it leads to very favorable results in terms of the behavior of time. So we would take this as evidence that the maximum possible entropy is infinite, but we don't really claim that that's a fact. If the maximum possible entropy is infinite, then one has the simple statement that any state of finite entropy is then a state of low entropy, because it's low compared to the maximum possible entropy, which of course is infinite. So this sounds like a very simplistic idea, but I will argue that I think it really has teeth and does allow us to have a fairly simple way of getting around Don Page's argument and showing that it is indeed possible for an arrow of time to develop in a universe in which the laws of physics are completely time symmetric and in which no special assumptions are made about a low entropy initial state. So the idea is that the entropy can increase from any given starting point under these assumptions. And that means that the metaphor of the gas in a box, which I talked about a few minutes ago, gets replaced by a metaphor of a gas without a box. Okay, so now I'd like to describe a detailed toy model of this kind of a system. We're claiming really that we think the basic results that we're talking about would probably hold in any system with Hamiltonian dynamics, but we'll illustrate it, proof of existence, proof of principle, by considering the simplest possible model that we can construct that has, that's complicated enough so we can talk about entropy. And that model is simply a gas of n particles, where n is some large number, and we'll just let them be non-interacting particles moving in empty space. That's all we need to illustrate the ideas that we're trying to convey. So we want to imagine choosing initial conditions for the system by just making up any old probability distribution for the positions and a second probability distribution for the velocities. And then we want to essentially imagine using a random number generator with those probabilities built into it to draw a random set of initial positions and initial velocities for each of these n particles. And then we want to describe how that system will behave. So this is the system. We choose an arbitrary probability distribution for positions, an arbitrary probability distribution for velocities, and then we generate a configuration of n particles based on those probability distributions. Okay, now a key point, which you may think is obvious, or many of you may not, I don't know what to expect, but we want to insist that these probability distributions be normalizable. Probabilities must add up to 1. And I think if you look at any mathematics book about probability theory, that's axiom number 1. But still some physicists are skeptical about it, and I'll talk about that a bit more. This rules out ill-defined options, such as, for example, a uniform probability to be anywhere, which is what some physicists have told me when I tried to describe this. Why don't you just assume that the particles are equally likely to be anywhere? So yes, that does mean that I am really saying that a uniform probability distribution is simply not logically possible. And the point is that it leads to immediate contradictions. And that's why the mathematicians always insist that probability distributions be normalizable. So the simplest contradiction that I know of, there are really many that one can talk about, but suppose that I could imagine a random number generator that was equally likely to generate any real number. To generate a random number where the probability distribution is just flat on the entire real line. So suppose then that we used it to generate two numbers called A and B in succession. And then suppose I ask the question, what is the probability that the magnitude of B is bigger than the magnitude of A? What I want to argue here is that one gets two contradictory answers here, depending on how one chooses to look at the question. The first method is to say that A and B are equally likely to happen in either order. If you have a random number generator, it is by definition generates a random number that's independent of all previous numbers that it generated. So it doesn't know or care whether it's generating A first or B first. The probabilities are exactly equal to generate A and B in either of the two orders. And since both orders are equally likely, the probability that the magnitude of B is bigger than the magnitude of A has to be the same as the probability that the magnitude of A is bigger than B, because they're interchangeable. And that means that both probabilities have to be a half. So by this argument, the probability that the statement magnitude of B is bigger than the magnitude of A must be exactly a half. On the other hand, if we imagine that A was generated first, which is the way I originally told the story, then there's only a finite range of numbers with magnitude smaller than A. That is, B would have to be between minus the magnitude of A and plus the magnitude of A to have a magnitude that's smaller than the magnitude of A. But there's an infinite range with larger magnitude. B can be anywhere outside that range. So by this argument, we would conclude that the probability that B is bigger than A is 1, because there's infinite length of line where this would be true and only a finite length of line where it would be false. So it's contradictions like this that have persuaded mathematicians that it just makes no sense to talk about a probability distribution that's uniform on the real line. It's just simply not conceivable. The only probability distributions which are logically consistent are normalizable probability distributions. I want to mention here that I learned this particular paradox from Aaron Wall, and I think it is really a very lovely paradox that very clearly illustrates what the problems are. So let's go back to our toy model. We're going to assume probabilities that are normalizable, ruling out ill-defined options such as a probability distribution that's claimed to be uniform on the real line. Normalizability implies that the distribution of particle is localized, even though we did not assume localization. We're just assuming normalizability. it must be possible, therefore, to draw a sphere that's big enough so that the probability that all n particles are inside the sphere is 99.99%, or any number you choose. I'm going to be using 99.99% as just a prototypical number that's arbitrarily close to 100%. And if this isn't clear, let me just point out that as you make the sphere bigger and bigger, the statement that it's normalizable means that the probability of integrated over that volume approaches 1. That's really the definition of normalizable. So if we make the sphere big enough, it has to encompass an arbitrarily large fraction of the particles. And I will call that 99.99%. So here's a sort of a picture of what the initial distribution might look like. Particles in random places traveling with random velocities, but we can draw a sphere that's big enough so that essentially all of the particles are inside that sphere. And I'm going to be calling that the 99.99% sphere. Now what we want to do is let the system evolve. And remember that we just assigned these velocities at random. I didn't mention it, but we probably want to assume an initial velocity distribution which made the probability of any velocity v exactly equal to the probability of minus v in order to ensure that our initial conditions are not building in any arrow of time. For anything that has some non-zero probability, the time reverse state should have an equal probability. So we can do that, and we'll imagine that we did. We then have a random distribution of velocities here, and if we tried to calculate the entropy of this and how the entropy is changing, it might be increasing or it might be decreasing. We did not build in any arrow of time, but there'll be random fluctuations in our choices. But we would not expect any significant arrow of time in these velocities because they were chosen from a probability distribution that was time reversal invariant. The probability of v was always equal to the probability of minus v. Okay, now what we want to do is let them evolve for a long time and discuss what happens next. So the particles just have fixed velocities, so they just keep traveling on straight lines. Since the typical velocity has some value, whatever it is, we can wait for a length of time that's long enough so that the distance traveled at that typical velocity is much, much larger than the radius of our 99.99% sphere. And then the picture will look like this. Almost all of the particles will have left that sphere, and they will all be traveling outward from the sphere in different directions. And at this point, we can easily see that the system has developed an arrow of time. This picture does not look at all like it's time reverse, which would be a picture where all the arrows are pointing inward. So very clearly, the system has become time asymmetric. The picture itself shows a very clear distinction between the future, where the particles will be further out, and the past, where they'll be further in. I'm not going to try to talk in detail about entropy here, but one can define a coarse-grained entropy, and one can easily show that the coarse-grained entropy does grow as the gas moves outward. I didn't put it on my slides, but I'll say a few more details about that. One way of defining coarse-grained entropy, which I think is the simplest, is to imagine that there's some finite resolution in x, I'll call it delta x, and some finite resolution in p, I'll call it delta p. One can then divide phase space into rectangular solids whose dimension of each little block in position is delta x, and the dimension of each little block in momentum is delta p. As you probably know, the fine-grained entropy, if you just take the entropy of the system, not making any simplifications, is automatically conserved under Hamiltonian evolution. But entropy increases because of this coarse graining. You admit at some point that you can't measure everything with infinite accuracy, so one has to make an approximation to the probability distribution. The approximation that I have in mind here is simply taking into account these finite resolutions and taking the original probability distribution, whatever it is, and coarse graining it by setting the probability density equal to a constant within each of these rectangular solids. And you adjust that constant so the total probability of being in that phase space volume is the same as what it was in the original distribution, but now you've smoothed it out by making it uniform within these rectangles. If you do that, you can see how the coarse-grained entropy increases, because if you go out further, I'm sorry, let me take one step back and say that the fine-grained entropy is constant because as these particles spread out in position, the range of momenta associated with any given position goes down with time. That is, the velocity has to be more and more precisely tuned to end up in this region if you're going to wait a very long time. And that's how the compensation works that keeps the fine-grained entropy constant. But what happens with the coarse-grained entropy that I just defined is that eventually the range of possible momenta gets to be smaller than the resolution, and then you don't notice the range getting smaller and smaller anymore if you're looking at the fine-grained entropy. So what one sees is a constant range of values in momentum space with an increasing range of values in position space, and the coarse-grained entropy then increases. That was somewhat more technical than the rest of my talk. If you lost me, now you can wake up again. I'll come back to saying things that are hopefully clearer. So the conclusion now is that if we evolve the system forward in time, entropy starts to grow, trying to approach its maximum value, but its maximum value is infinity, so it never reaches it. And a clear arrow of time develops and should persist forever, going upward in this picture. Now, a curious feature is that if we evolve the same system backwards in time, it would behave exactly the same way because everything is time reversal invariant. So at large negative times, again, the particles would be moving outward if we showed the movie backwards in time, but moving inward if we showed it forwards in time. And the arrow of time would point the other way. So we'd have an arrow of time in both regions. Bottom line, for a finite amount of time near where we started, there is no definite arrow of time, and that's what I meant by the question mark here. But at some time in the future, an arrow of time develops, as we showed on the previous slide, and points towards the future, while in the past, an arrow of time develops pointing backwards. So this kind of universe exists for all time, and the arrow of time is well-defined in the past, well-defined in the future, ill-defined in the middle. But notice that the middle is only a finite range of time, while the future is an infinite range of time, and the past is an infinite range of time. So almost everywhere, there is a well-defined arrow of time, in spite of the fact that the laws of physics we were using here, which is just inertial motion in this case, are certainly time reversal invariant. And the initial state that we designed was time reversal invariant. No special initial state needed to be chosen. So the ever-expanding gas that I'm talking about, sorry, this ever-expanding gas that I was talking about, this gas of particles, of course, is only a toy model, as I said at the beginning, and we are thinking of it as a metaphor, as a toy model that represents eternal inflation. That is, in many inflationary models, I would say most inflationary models, once inflation starts, it never completely stops, but rather there's a continuing inflating region that survives forever with universes forming within it. We call those pocket universes. And this, it appears, can go on forever. Don't have time to talk about it in detail, but that's what we really mean for this region to the future and the region to the past. Okay, so the summary so far is based on this picture. And what I've tried to show is that time-symmetric laws of evolution, even with time-symmetric initial conditions, can nonetheless produce an arrow of time, as in that picture. A key requirement for us was that the system has to be a system that has an infinite maximum possible entropy. Otherwise, the system would reach an equilibrium and the arrow of time would disappear. The arrow of time is two-headed, pointing to the future in the future and to the past in the past. And an important feature here is that the full space-time picture, as shown in this diagram, is still exactly time symmetric, which is what you'd expect since it was produced by time symmetric laws of physics. And by time symmetric, what I mean is if you take this diagram and turn it upside down, it looks exactly the same, except that the labels would have to be changed. But the arrows point the same way, and the question mark is still in the middle. So globally, this picture of a possible multiverse or universe is completely time symmetric. But nonetheless, in any given location, there's a well-defined arrow of time, and the direction it points depends on where you are. It points to the future in the future and to the past in the past. Okay, that actually is the main part of my talk, but there are a couple other topics I'd like to talk about that are closely related. So I thought they would be fun to talk about. One question I wanted to address is whether or not fine-tuning can be explained in the context of Hamiltonian evolution. Some people have argued that it's not possible and have used that as an argument against various theories of evolution. Their favorite seems to usually be inflation, although it applies equally well to any theory of evolution. But what I will argue is that if the phase space is finite, the answer really is no. And this is, in fact, the argument that I think people have in mind when they raise this question. There's a famous theorem in classical mechanics, Liouville's theorem, which says that if a system is known to lie within a specific volume of phase space, and then you allow the system to evolve, so it moves in phase space, the volume does not change as the system evolves. It's invariant under evolution. So that means that time evolution merely pushes the probability distribution around in phase space, but can never make the probability distribution more tightly constrained or less tightly constrained. So what is improbable at one time, because it corresponds to a very small volume in phase space, that's basically what we mean by improbable, is equally improbable at all times, because the volume that a probability distribution takes up in phase space simply doesn't change with time. So the only way it could be confined to a narrow region at late times is if it's confined to a very small region at early times. So with a finite phase space, I think this is absolutely true. One can never explain the fine-tuning of any parameters as the result of Hamiltonian evolution. But if the available phase space is infinite, then I think it's very easy to show that the answer is yes, fine-tuning can be achieved. And I will show that by showing you a simple model. Suppose the Hamiltonian is that, just minus p times q. And might add that this is really an upside down harmonic oscillator where p and q represent the original x plus p and x minus p. But you don't need to know that. All you need to know is how to calculate the Hamiltonian equations of motion, which are given by p dot is minus the partial derivative of h with respect to q, which, as you can see, is p. And q dot is equal to plus the partial of h with respect to p, and that's minus q. So we know how to solve these very simple differential equations. As the system evolves forward in time, p has a probability distribution which grows exponentially in time. In fact, any given instance of p grows exponentially in time. But q does the reverse. It decreases exponentially in time. So if we allowed the system to propagate, q becomes fine-tuned to become arbitrarily close to zero. And this does require the infinite phase space because as q becomes fine-tuned close to zero, p has to grow without bound to allow the total phase space volume to be fixed, which is required by Liouville's theorem. So yes, fine-tuning can happen. I now have one other thing. When I first showed this to people, some people said, oh yeah, you could do that for the Hamiltonian you showed, but the Hamiltonian show is not positive definite, and Hamiltonian should be positive definite. So I brought that to my son Larry, who's a great mathematician, and he immediately came back with a way of modifying it that would allow the Hamiltonian to be bounded from below and still have this property. So here it is. I want to skip this discussion on how effective the fine-tuning is because it gets kind of technical with epsilons and deltas, but maybe I'll just summarize it in vague words. The answer is that if you're willing to wait arbitrarily long, how long you have to wait depends on what the initial probability distribution is. But if you're willing to wait arbitrarily long, then the fine tuning is as good as you want. Specifically, you can make the values of Q that you will accept to be arbitrarily small, and you can make the probability that Q will end up being in that range arbitrarily close to 1. So the fine tuning really is as good as you could request, as long as you're willing to wait long enough. Okay, now I want to move on to one more topic, and this will be the last in today's talk. Suppose we assume, contrary to the assumption that I was using in today's talk, suppose we assume that the universe has a finite available phase space. Does that cause any cosmological problems? And I want to argue that the answer is emphatically yes. That appears to be a cosmological disaster from the way we are looking at it. So suppose, for example, that reality can be described by some quantum system which has a maximum possible entropy. Then the system will reach thermal equilibrium according to all the standard lore, and will then undergo Poincare recurrences forever. And that will mean that all microstates will occur and reoccur with equal probability. That's what thermal equilibrium looks like from a microscopic point of view. Now, does that mean that complicated things like life will never happen in this phase? That's what people often assume. Life doesn't really exist in thermal equilibrium, but that's not really quite true, because all microstates occur and reoccur an infinite number of times, and that includes microstates that have living beings in them, just like me and you. So life, including observers like us, will in fact continue to occur in the thermal equilibrium phase. But with overwhelming probability, the worlds that they will observe will look nothing like ours. And this is sometimes called Boltzmann brains. And it's really exactly the issue that I spoke about at the beginning of this talk when I described the differing opinions of Boltzmann versus Feynman. Feynman was basically making the argument that I want to make here, that if you have a thermal equilibrium mix extending in time arbitrarily far in the future, yes, there will on rare occasions be rare things like planets or just isolated human brains, but on average they will always be surrounded by a thermal equilibrium gas. They will not be a reality that will extend over huge distances, but they will exist. And the point is that if this were the situation, it would mean that most brains, and I mean human brains, like in my head, brains that are exactly like mine, will continue to occur and reoccur far into the future, infinitely far into the future in this thermal equilibrium mix. And that's what cosmologists today refer to as Boltzmann brains. And that means that given that I have a brain that acts exactly like it does and knows exactly what it knows, I can ask, am I likely to be near the Big Bang, or am I likely to be far in the future in this thermal equilibrium mess? And the answer is, if the universe reaches thermal equilibrium and stays there forever, I'd be far more likely to find myself in the thermal equilibrium phase, where my brain would just be a Boltzmann brain, just one of these thermal fluctuations and microstate that occurs once every Poincare cycle. So this is very different from our view of the world, which is fundamentally historical, fundamentally based on the idea that we originated in the Big Bang 13.8 billion years ago. That's how we understand the universe. In thermal equilibrium, however, probabilities are determined only by state counting, because every state counts equally likely. So for example, we can imagine a state that looks just like ours, except that the temperature of the cosmic microwave background, that's what CMB stands for. We can imagine a world that looks exactly like ours, except that the temperature of the cosmic microwave background was 10 degrees Kelvin instead of 2.7, which is what we actually observe. There'd be vastly more microstates if the temperature were 10 Kelvin than 2.7 Kelvin. And that means that if we're living in the thermal equilibrium phase, we should be much more likely to measure 10K than 2.7K. And this was pointed out in I think, a fabulous paper by Dyson, Klebin, and Susskind in 2002. So if entropy has an upper limit, I think there's no way to get around the quote prediction that 10K would be much more likely than 2.7K for what we should expect to see when we look up in the sky and measure the cosmic microwave background. But if we use the historical approach, assuming that we really are evolving from a Big Bang, then we can calculate what we expect the temperature to be. And given other conditions now, we can calculate the temperature expected and we get 2.7K. And that is the scientific point of view that's current. However, if the semi-classical global picture of eternal inflation is valid, which is what I was advocating, is what we really mean by this future of ever-increasing entropy, then new pocket universes would be constantly being created. Each of those would be created from a local Big Bang. Poincare recurrences would not happen in the system because it does not have a finite phase space. And our historical understanding of the world would be justified, and everything would fit together nicely. So I'm ready to summarize my main points. First of all, and this was my main point, I claim to have shown that time-symmetric laws of evolution with time-symmetric initial conditions can nonetheless produce an arrow of time as long as the available phase space is infinite. And that was the main point. But then I had two separate points near the end. I also claim to have shown that Hamiltonian evolution, again, if the available phase space is infinite, can lead to the fine-tuning of dynamical variables. And third, I claim to have shown that if the universe is described by underlying physics with only a finite available phase space, then we would expect that we would most likely be living in a thermal equilibrium state that would be very different from the world that we actually observe. So I will stop there. Thank you very much. I'm told that now we can go directly into questions.
Okay. Thank you very much, Alan. That was fantastic. I think the situation with the questions is that the people who are the official panelists can see what is written, but the other participants in the event cannot. So perhaps I'll read out the questions and that you can also, I think, see, and then other people can answer. So hear your answers. So from Professor Norma Sanchez, is saying that the arrow of time is really a comment, I guess, but it would be interesting in your response to it, that the arrow of time should emerge from a quantum gravity theory that is from Planckian and trans-Planckian physics and quantum gravity entropy, whereas your perhaps starting approach is a mathematical idealization and perhaps semi-classical. So how might you respond to that?
I will respond to that by agreeing 100%. Certainly my description was semi-classical, and I did try to say that we don't know for sure that the phase space is infinite, but this does give, I think, a very attractive picture. And while quantum gravity is a wonderful thing to talk about, and I hope that someday we'll be able to really use quantum gravity to describe the universe, right now I think there are very few questions that we're actually capable of answering at the present time using quantum gravity. But nonetheless, the point is well taken. There's certainly plenty of room here for a more detailed explanation.
And then Seth Corrin writes, some have been motivated by quantum gravity ideas to expect that CPT should fundamentally be a gauge, i.e. local symmetry. Do you think this would intrinsically change the problem and or your solution?
Okay. Yeah, I would say that I would not expect that to change the problem or my solution. I acknowledged at the beginning of my talk that CPT appears to be exact, while CP alone appears to be broken. But I don't think that really played any role in discussing the mechanism that I was proposing for the origin of the arrow of time, which was described in the context of a theory of just particles moving in straight lines, which is certainly CPT invariant. So I don't think it really, I could be wrong, but I don't think that anything that I said would be modified by the fact that CPT is to be thought of as a local symmetry.
Great. Then Charles Bennett asked, is an open universe much more likely than a closed universe based on available phase space? This sounds like a potential bet to me.
Right. Okay. Well, I think, the picture that I'm advertising, but did not talk about in detail, is the picture of eternal inflation. And in eternal inflation, individual pocket universes look slightly open. And it's highly, highly improbable for them to have enough of a fluctuation to resemble a closed universe. But of course, if there's sufficient inflation, they look very close to flat. If we talk about the entire multiverse as a system, I think neither the word open nor closed applies. The words open and closed are sort of uniquely defined if one talks about universes that obey the Robertson-Walker metric, or described in words, universes that are assumed to be homogeneous and isotropic at the start. Those can be classified uniquely as being open, closed, or flat. But if you allow a universe that's just lumpy in all kinds of ways, which is really what our picture of the multiverse would be, then I think one really can't pin it down as being either open or closed. But the individual pocket universes should look open.
Thank you. So then Emil Prodanov asked, does the current accelerated expansion constitute inflation?
Well, I guess I'd say yes and no. It certainly is a similar phenomenon, and the simplest explanations we have for it make it look mathematically very much like inflation. The simplest explanation for the current accelerated expansion is vacuum energy, and vacuum energy behaves very much like the energy of a scalar field that we imagine in the early universe to drive inflation. So certainly the current accelerated expansion is an example of the fact that general relativity does allow repulsive gravity, which is exactly the mechanism that inflation takes advantage of.
Great. Okay, then the next question is from Chaim. Please excuse my pronunciation. And thanks you for a very informative talk, which I certainly agree with. And this person's asking a more general question. So what are the big picture kind of thing? What are some of the problems that you foresee cosmological physicists will need to tackle in the coming years?
Okay. Okay, of course, it depends what type of cosmological physicist one is talking about. Certainly from an observational or phenomenological point of view, there are huge questions associated with, for example, what is the dark matter, which makes up some 30% or so of the total energy density of the universe, and what is the dark energy, which makes up some 70%. There's really 5% left over for ordinary matter, so I didn't do it quite right there. But about 70% of the current universe is what we call dark energy, which is simply defined as the stuff that's causing the universe to accelerate. The simplest explanation for the dark energy is that it's just vacuum energy, energy of empty space, but we don't know that for sure. I would very much like to know the answer to that question. And if the answer is that it's vacuum energy, that leads to further huge mysteries, really, because as a value for the vacuum energy, it's a number that's vastly smaller than what we know how to understand. We would expect a number that's about literally 120 orders of magnitude larger than the vacuum energy that we infer from the acceleration of the universe. So there are huge mysteries there. For physicists like myself that think more about the very early universe rather than the present universe, there are huge questions associated with this process of eternal inflation, which I mentioned. Because eternal inflation leads to universes that keep growing exponentially forever, it turns out to be very difficult to define probabilities in eternally inflating universes. One is always comparing infinities. Anything that can happen in an eternally inflating universe will happen an infinite number of times. So to decide that some things are rare and some things are common involves comparing infinities in a way that we still don't fully understand. So there are lots and lots of questions of all different levels that cosmology will be wrestling with for some time into the future.
It's always good to hear that cosmologists can be kept busy. Yes.
Right.
So the next question is from Sapphire Lally, who also thanks you for your fantastic talk. And they have a question. In the toy model you presented, do long time states not tend to the uniform probability distribution you ruled out via contradiction?
Okay, interesting question. The answer is yes and no. If we start with the probability distribution that's normalized for some distribution of particles and let it evolve, it will in fact spread and spread and spread. That means it will point-wise literally be approaching a probability distribution that's zero everywhere at any given location. The density probability will go to zero, but at any given time it's normalized. This is a situation where the limit of the probability distribution as t goes to infinity simply doesn't exist. Probability at any given location goes to zero, but that's not a probability distribution at all. So limits don't always exist, and I think that's really the way that one gets out of the paradox that Sapphire is asking about.
Great, you are spurring a lot of questions here. So Josh Ehrlich asks, if the phase space probability distribution is not time independent, then what determines the initial probability distribution?
Okay, well, certainly I'm not claiming to know, but what we are claiming is that the initial probability distribution really doesn't matter. And by initial, the word initial has to kind of be redefined here because our system exists for all time. But the time in the middle where the entropy is the lowest, where in our toy model we made up initial conditions, we can consider that to be logically the initial condition, even though it's not chronologically the initial condition, because we do want to imagine evolving in time in both directions. We really have no idea what determines it, but our argument is that really no matter what you have, entropy will start to grow, and we assume, but don't really claim to be able to show that that will lead to inflation beginning somewhere, and then eternal inflation taking over.
David asks, does an infinite phase space require an infinite universe in the sense of either being infinitely large or being infinitely old?
Okay, the universe that we're thinking about does evolve forever, so it will become infinitely old. That's really just by assumption. I'm not sure we even need that assumption, but it's the way I described it and the way we think about it. And if it's eternally inflating, it may or may not be considered infinitely large at any given time. One issue about talking about the size of the universe is that special relativity tells you that if 2 points are further away than a light signal can get from one to the other, you can't really tell which is in the past and which is in the future of the other. So the notion of what you mean by equal time in a general relativistic situation is largely a matter of choice, and therefore deciding what the total volume is at any given time depends entirely on what you choose to call equal time. So the question is somewhat vague, but certainly the model universe that I have in mind is one that can grow without limit. And that's the minimal requirement for this infinite or unlimited available phase space, that it can grow without limit.
Well, indeed, it seems that the next question from Barbara Drossel is right on this issue. If the universe expands forever, due perhaps to dark energy, phase space increases without bounds, and doesn't that imply that phase space is indeed infinite?
I think I'll admit that maybe it's true, but I'm not sure that it's true. Certainly it is possible for a quantity to increase without bound while still being finite at any given time. The variable t itself increases without bound as t gets larger, but at any given time, t has some finite value. And if the volume went like t squared at any given time, it would be finite, but still unbounded in time. So, so I think there are at least toy models where it's possible to increase without bound without ever actually being infinite.
Right. Patrick Desgupta also thanks you for your thought-provoking talk, and then makes the statement, in your toy model, the particles were non-interacting. If one switches on interactions, would there still be two arrows of time, one to the future and the other to the past?
Okay, the answer is we think so. We think it's a generic feature of any form of Hamiltonian evolution. What it depends on is sort of the general law, which is that if the entropy of a system is lower than the maximum possible entropy, on average, such systems will evolve towards higher entropy. And that's the phenomena that we certainly see around the world. I think we can even prove that that's how things do behave, at least in simple models. So I think interactions do not really change it, and that our toy model is generic in that feature, that entropy will increase if it's less than the maximum.
Unfortunately, I skipped one here. Andreas Albrecht asked, do you feel infinity should be defined as limits of finite quantities? And if so, it seems that your approach is based on a very special ordering of limits. So, I mean, I think there's a subtlety about limits here. So,
right.
How would you comment here?
Okay, I guess I don't think that infinities have to be defined as limits of finite quantities, although I think often they can, and often that's helpful. But I think we do know mathematically how to talk about the real line, how to construct an arbitrary point on the real line. And I don't think we have to think of the real line as being a finite line that's getting longer and longer. So I don't believe that it's necessary to consider all infinities as limits of finite numbers.
I feel for you to have given a wonderful hour talk and then have an hour of questions. But you provoked too many thoughts. So then next question is from Saloni. Could it be feasible that the two-headed arrow of time be contemplated with the concept of wormholes? Is it?
Yeah, I would say, oh yes. I think it's independent of things like wormholes. I don't see why wormholes could not exist in a two-headed arrow of time picture.
Okay, great. Paul Halpern then asked for the physical motivation of the Hamiltonians you proposed, particularly the one with the arctangent.
Oh, I think I would just say that those were only intended as proofs of existence, proofs that it is possible to fine-tune parameters. Maybe I should have tried to explain the generality of it, starting without the arctangent, which was really just put in to answer people who said, oh, I think Hamiltonian should always be bounded from below. But the original Hamiltonian that I showed, which was just h equals minus pq, really is just an upside down harmonic oscillator. But by a canonical transformation, I think literally any system which has 1p and 1q can be brought to that form. So I think the example that I showed really shows that if you have any Hamiltonian system, maybe I only showed it for 1p and 1q, but I think it generalizes. But if you have any Hamiltonian and you want to fine tune any combination of p and q, I think you can always do it to whatever accuracy you want, as long as you are willing to wait.
Okay. So Fabian Wagner asks, doesn't the emergence of an arrow of time crucially depend on the fact that there is a finite number of particles put into an infinite volume? What would you think might happen if there were with an infinite amount of particles?
Okay. I guess the answer is that I think it's possible to avoid what I'm talking about with an infinite number of particles. With an infinite number of particles, you could have them uniformly spread on the entire real line. You could have a probability of a fixed probability of a particle existing in any given interval. And that system just starts in thermal equilibrium and will stay in thermal equilibrium. So important really, maybe I should have clarified, we're assuming that there's no maximum entropy to the universe, but we are assuming that at least in the logically initial state that we construct, the entropy is finite and therefore automatically less than the maximum entropy. So if you started with an infinite number of particles, the initial entropy would presumably be infinite, and you would not be able to construct the scenario that I discussed.
You're doing fantastically. So how did shrinking models as opposed to inflationary models for a universe explain the arrow of time? From Shorei Siamauji. Please excuse my pronunciation.
I think I'll just say, I don't know. So we should have somebody who advocates the shrinking model.
So yes, I think this we perhaps are encountering an issue of you having such a thought-provoking and such a large number of attendees that I'm pounding you with questions. I do feel that now might be, since you've had like 20 minutes of questions, I think it might be time to give us all the opportunity to thank you very much for a wonderful and thought-provoking talk that did indeed prove as a wonderful memorial again to Andrew Chamblin. So thank you so much, Alan, for agreeing to give this talk and for giving such an inspiring talk. And thank you to all the participants, and my apologies to those of you who've put in a question that we haven't had a chance to answer. But thank you so much to all, and well done.
Thank you.
And so once again to all, wrong button. Once again to all, we will distribute to all the signed up registrants where the recording is once we have put it on our website. And so thank you again, and all the best to the holiday period, and please may 2021 be a major improvement. Thank you very much.
Thank you.